Hi everyone, my name is Shai. I'm a consultant at freelance developer. I'm going to talk today about property-based testing. I want to start with the reason that this is an important subject in my opinion. So most of my experience is relatively long periods of time. Most of my experience is relatively long periods of time at the same company, mostly development and architecture, but also some product and management. So I had a lot of opportunities to be a part of projects right from the beginning and until the project was already mature. So it's an opportunity to look at relatively complete, finished projects and ask what went well here and what didn't. What are some key factors that really made an impact? And one of my main conclusions from all of this is that testing is a very successful strategy. It's true that there's some nuance, but as a general rule, 80-20, when we take some area of the code and we write a strong test that makes sense for the situation, everything about that code tends to play out without too much drama. We get a fairly good development velocity, stability, a short feedback loop, and a bunch of other good stuff. And I've seen this happen really with a bunch of areas of the stack, different languages, different types of projects, everything. Now, the fact that strong tests are useful probably doesn't surprise anyone. It's not that we don't understand that they're useful, we do understand it, but we also understand something else. Strong tests are also expensive. So in a lot of the projects, while we're building the project, it's not really obvious that it's going to be worth it, so we don't write strong tests. So if we want to be able to afford it, we'd like to be able to invest less in creating the tests and still get strong tests that check the things that are important to us. Work less and get more. And property-based testing is a technique that aims to help us with this. ROI. For some given amount of investment in tests, we'll get much stronger tests with all the advantages. We'll start with an example, sorting a list of integers. Now, sorting functions are the hello world in property-based testing. Not the kind of code that you write every day, just an example that makes it easy to explain the basic concepts. So how would we normally test a sorting function? We'd write a bunch of test functions that look sort of like this. Have some specific input, run the code over it, and then check that the output is what we expect. And we'll just write a bunch of tests like these every time, take a specific input, run the code, and make sure that the output matches what we expect. And even here, we're going to need to work pretty hard to test the function well. And the reason is that sorting functions tend to be pretty complex things, and there's a lot of dealing with indexing and stuff like that. And maybe we've written larger equal instead of larger somewhere, and it only shows up in very rare cases. So this is where property-based testing comes in. The basic idea is that the computer will help us find cases where the code is incorrect. The process is that we as developers describe the input and the output, and the computer tries to find for us counterexamples. Cases of inputs where the output doesn't match the description. In more detail, we describe the input and output, meaning we write code that generates inputs. For us, it's going to be a list of integers. And we describe the outputs, meaning we write properties or conditions on the outputs. For this example, we're going to define two properties. The output of a sorting function is a list that, one, it's ordered from small to large, it's sorted, and two, it contains exactly the same element as the input. Now the computer will take our definitions, generate a bunch of inputs, on each of them it will run the code, and on the outputs that it gets, it will check the conditions, our properties. By the way, these properties that we define and the computer checks, that's the origin of the name property-based testing. Right. The good ROI for property-based testing comes from the fact that this process tends to create tests that are pretty good at catching bugs. And for this to happen, we need two things. One, we need the inputs to be diverse enough to actually catch edge cases. And two, we need the properties in themselves will be pretty strong. And strong in what sense? Well, because we're not checking that the outputs are exactly equal to some specific predefined value, but instead of checking a condition, there can be a case that an output is wrong, not correct, but the condition doesn't catch it. And we're always looking for properties that make it almost impossible or impossible for any wrong output to pass the test. It's a significant challenge, and we'll dive more into it later. For now, let's look at what it looks like for our example. And are these properties strong? And the answer is that they're not just strong, these properties are actually complete. This is really sort of the definition of what it means to be a sorting function. So for the sorting function, it really is the same as if for every input we spelled out the exact output that it should be, that the sorting function should give us. And the meaning of this is these tests are very strong and very good at catching bugs. If the inputs are diverse enough, it's pretty much impossible to write a wrong implementation that still passes the tests. Okay, to make stuff complete, we'll see a few code examples. Everything you see, every code example you see, and everything that I talk about, even if I'm not showing the code, there is a repo in GitHub with the code and running instructions that you're more than welcome to download and play with. I'll give a link at the end of the talk. As fitting for PyCon, my examples will be in Python with the excellent hypothesis library. But probability-based testing is not just a Python thing. Chances are that every other language you're working with also has a similar library, so you can take this and use it anywhere. Okay, so have a look at a sorting file, at the first test. Test the sort of results is ordered, that the list is actually sorted after we call the function. First, we define the input as the list of integers. This is done by the function getting a parameter, this list here, and where is it coming from? The given decorator above. We can see that the hypothesis gives us built-in helper functions to generate random lists, where each list is composed of integer elements. Okay. In the body of the test function, first of all, we call our code to get the output, and then we need to check the condition, the property of the output. And unsurprisingly, checking the condition here is just going over the output, the list one by one, and checking that each element is smaller or equal than the element after it. Okay, jump your terminal and see some tests. It's going to be a challenge with one hand, but we'll see if we can make it happen. Okay, so yes, it was the last command. Right, so if everything's okay and there are no bugs, the tests look just like we expect. Then we get a test success that's winning. And I'm going to introduce a bug to the code. The focus is not what bug it is. I'm just messing up some index. So
cannot see the screen.
Can see the screen. Oh, I did not expect that.
Let's consider the bug.
Definitely. Yes. We good? Right. So yeah, I'll just okay. So I just okay. I'll put the microphone down for a second. Cool. And so they're just green if there's no bug, and I'll introduce the bug now. Just commenting the incorrect version of the code, running past PyTest again, and we can see that it fails. And there's quite a bunch of output here, and obviously with the font size in a live talk, it's difficult. So I started just the important stuff, and it's in the presentation. And we're good. Okay, so we can say that in addition to the actual failure of the test, we also have another piece of information. This is the falsifying example, an input for which the test fails. And we can see that the list that we got here is fairly short, and also that it's composed of relatively simple elements, right? 1, 0. And this didn't happen by accident. It's a result of something called shrinking. Now, normally in this process, when a test fails initially, it's with some relatively complex output, maybe something like the one that you see above here, and actually, usually it's a lot more complicated than that. And so it will be easier to diagnose and debug and understand what's going on. Hypothesis will try to find for us the most minimal, simple input that still fails the test. And because a lot of the time our functions or things, the APIs, the things that we test, they receive a lot of different parameters. They can be very complex. The fact that we have the very minimal, very smallest, simplest input example that actually fails the test really helps us out and makes it easier for us to diagnose and understand what's going on. Okay, quick recap after we've seen the example. the basic idea for probability-based testing is that the computer will help us find cases where the code is incorrect. We, the developers, describe the input and describe properties, conditions on the output. The computer takes a description, runs the code, runs the code and gets the outputs, and then checks the properties, the conditions on the output. If a bug was found, the test fails, we shrink it. So we find simpler examples to work with. What are the benefits that we saw in this example? Wasn't a lot of work, right? Fairly simple functions, just two test cases. The tests were fairly good at catching bugs, no matter what we throw at it. And the shrinking gave us very simple counterexamples to debug. Okay, so we've tested one function. Obviously, it was just in a hello world, so it's not really a realistic piece of code. But of course, we want probability-based testing to help us with the code that we actually write. And if there's one thing I'm saying and you take away from the presentation, it's the probability-based tests are a good match for code that works in real life. They combine well and really help us in a lot of types of the tests that we run. To demonstrate this, we're going to invest a big chunk of this talk showing an example of a scenario that's both really common in the real world and causes issues in the real world. The scenario is that we want to test some API which relies on a state, and we need to somehow take the state into account when we write our tests. The challenge with this kind of thing, testing this kind of scenario, is the complexity of the test cases that we need to create. The behavior of the code and the bugs are the result of, a lot of the time, the result of complex interactions between multiple API calls. So writing tests really cover this well. Can be, first of all, it's a lot. It's a lot of different possible combinations, and it might also be very complex to think of the scenarios. It's just a lot of work. We're going to use a technique called stateful testing. It's a slightly more advanced technique and takes some more work to set up, but the advantage is that it helps us deal with this kind of scenario. And we're going to explore the technique using an example, a simple crowd application. And the example is going to be simple. It's going to be a simple application because we want to be able to follow along step by step as we create tests that actually catch bugs. But stateful testing looks exactly the same, even in much more complex scenarios. It's good really for every case that we have some API that we test, and behind it there's some state that we need to think about. Right. So just for a second, the example is going to be a web application, small web application. It's a list of books, and I'll jump in the browser for a second and show it. So we can, like expect, we can add a book, and we can update it or delete it. Simple stuff. And the application works against a backend server, local HTTP server, which supplies the actions that it needs. And we're going to test this server. We're going to send HTTP requests to it, and we'll check the responses. What's the basic idea behind stateful testing? So let's say we want to test an API, and it can be anything from a class where the state is a simple integer, and we test it by calling the class's methods. It can be a full-blown application in the cloud. The API provides a set of actions, and what we do? The API provides a set of actions, and what we do is we define these actions. We write code that drives them. So for this example, it's going to be calling HTTP requests on the local server. Now, Hypothesis is going to take the definitions, the actions that we define, and create random sequences, and then each sequence to run action by action against the server. And we'll generate sequence after sequence of these until we reach something that fails a condition, that shows us the test failed because some condition was false. And we can say that in this case, the failing sequence contains quite a lot of actions, and probably not all of them are needed for the test to fail. So here too we'll use shrinking. Hypothesis will find for us the very minimal example, very minimal subsequence of actions that still fails the test, and this is what we're going to get for debugging and diagnosing. Okay, so we said that we generate random sequences and we check conditions. So let's say we want to check, we just ran this example, this action, and we want to check a condition. We want to check if the API response was correct. Here we have a problem because the response for this API action might be dependent on everything that happened before. For example, if this action is a list books, the response for list books is dependent completely on all the new book and the list book that happened before. So if we want to write conditions that make sure it's correct, we need to somehow take into account all this history. What do we do? And what we do is that in addition to invoking API calls and checking the responses, we'll also maintain a model with some state which is represents a part of the system. And we'll check the responses from the API against that state. To do this, we need to define a few other pieces of information. So we said we are defining API calls, which actions exist in the API, stuff like list book, the list book, new book, things like that. And we also need to define a bunch of other stuff. First, we want to define the state. This is a piece of data that represents a part of the system. And we're going to start with a very, very small state, single integer that describes the number of book count that we expect going to be in the list. We also need to define state transitions. These are, this is the way that we expect actions to affect the state that we define. For example, when we call new book, when we add a book to the list, we expect the book count to increase by 1. If we call the delete book, we remove a book from the list, we expect the book count to decrease by 1. Last thing we need to define are the conditions. Those conditions, this is what needs to be true after every API call. It's actually code that compares the response of an API call to the current state of the model.
What about error flows? For example, if I try to delete a book when the list is empty.
So we model that as well. We can do a Q&A later, and I'll dig into it in more detail. So, for example, the post condition that we'll start with here in the example is that when we call list books, we get the list of books, and we expect that the length of the list will be exactly the book count that we maintain in the model. See everything together. We define which API actions exist and write code that drives them. We define state that describes a part of the system, state transitions, which describes how the actions are expected to affect the state, and post conditions, which is a way to what needs to be correct after every API call, meaning something that compares between the API call result and the current updated model, the state. How does all of it come together? Let's say we have our API, our initial state, and the first action in the sequence. We call our API, receive an API result, then we update the state using the state transition, and then we want to compare both of them to see if something went wrong, so use the post condition to compare. Call the API, update the state, compare. And call the API, update the state, compare. We do this for every action in the sequence. Call the API, update the state, and compare. Again, next action in the sequence, call the API, update the state, and compare. Let's try the first test, put the definitions in the table so we can easily see it. First of all, our state, like we said, single integer describing the length of the list of books. The first action is new book. The transition for new book, the way that it updates the state is to increase the book count by 1. We don't check any condition on a new book. And the second action is list books. It doesn't change the state of the system, so no transition. But on the list books, we define the condition that we talked about. The length of the list that we get back from the server should be the same as the book count that we get internally in the model. Right, so pretty weak tests. Haven't written a lot of interesting stuff, but let's try it and see what we get. I see that already on the server. Okay, it's running. We can also see like HTTP logs here. So running. I'll just run the tests. calling this can take a few seconds, 5-6 seconds or something. Let's speed it fast here. And again, by the way, we could see, if we would look at the server test, we could see that there are a lot of new calls here because it bombards the server with HTTP requests. And again, we can see the test fails. It found some bug. Like before, too much output for the terminal. So I extracted just the important stuff to the presentation. And we can see that we got a list of books from the server that had a single book, although we expected it to be 2 books. And like we said, hypothesis will give us the minimal sequence that reproduces this issue. And the sequence in this case is that we created a new book with author A and title A. Then we created another book with author A and title A, same parameters. And then we called list books, and the condition already failed. So pretty weird, but let's try to see it in action. We have, let's see, this is clean. Yeah, okay. So we have the application. Let's do the actions that we got from sequence. New book with author A and title A. Yes, here it is. And another book with author A and title A. And nothing. Didn't add a book. Okay, so the test was right, and the staircase does reproduce in the application. And I'm not going to dive into it. So it's not a focus. So I quickly say that the bug is that every time we add a book that has the same title as an existing book, the new book overrides the existing book. And this is the result that, of the bug that I introduced in the code, by planted in the code, is that the server used the book title as the ID of the book instead of generating a new dictionary, which is what you should do. So fix the code, run the test again, and they pass. And the rest I'll show in the presentation, the rest of the executions. Okay, so seeing one simple example, let's add more coverage, test more of the functions. Next example is going to be a lot less sterile to see the kind of stuff we actually run into when we work. So let's also test the delete book, right? Define also the delete book action. And for the delete book, what we need to do is we also define the delete book action, and the transition for it is that we expect that when we delete a book, the book count will be decreased by 1. No transition on it, no post condition on it, we're not testing anything. And let's run the test. But it looks simple, but when we go to implement it, we see that we actually can't call the delete book because the delete book needs an ID for the book. And it can't call the server without having an ID, and we don't have any ID in this table. So what we do to handle these kind of cases is extend the state. We'll also keep a list of the created books in the state, meaning a list of the created books IDs. And the new book transition, the new book action, whenever it creates a new book, it will save the ID of the new book that was created in the list, and the delete book will know to look at this list to get the IDs of the books that it needs to delete. Run the test, and it fails. But this time, it fails because we expected the book count to be negative. So obviously, that's a bug in the test, not a bug in the code. And what happened is that a sequence was generated that created a new book and then deleted the book twice, and we didn't handle this situation. So after adding the new book, the delete book decreased the book count by 1 twice, and it became negative and incorrect. And the way to deal with it is, again, the same idea of adding something to the state. And this time we'll add a list of which books we deleted. A list of IDs of the books that we removed, and delete book we know to manage it, we know to add books to the list of deleted books every time a book gets deleted. It will also know that if the book is not already in the list, if it was deleted, then we don't need to decrease the book count. Right. Also define the update book. For the purpose of this of the test, it's a very simple action because it doesn't change the expected length of the list of the books, and so there's no transition, and there's also no post condition. We won't check anything on it, and run the test again. Okay, fail again. Now we got a list with 1 book, although we expected it to be empty. What happened? And the sequence that we got is that we created a new book, then deleted that book, then we updated it. So clearly, how the book brings back to life a book that was deleted. Plug in the API, we need to fix it. Also, we're thinking whether or not this is something that's user facing. Can the user actually, is it a theoretical value that can the user actually experience it? I mean, after we deleted the book, it's not in the list, right? So can we update it? And the answer is that yes, although it's a little tricky. And let's see how this goes. So let's say we have our book here, right? A second, refresh. Okay, everything okay. We have a book here, and let's say we opened the application in another tab, or maybe another device, something like that, right? And so we delete the book here. And maybe in the other tab we didn't notice it was deleted, didn't refresh, and we updated it somehow, right? And now we get back to the original tab, and it's back. So that was a little sneaky, but the test caught it. Yeah, good. Let's stop for a second and remember what we had here. First of all, what we didn't have here. We didn't think about complex scenarios. Didn't think about creating two books with the same title. Definitely didn't think about opening the application in two tabs in the browser, deleting in one, and updating in the second. Also didn't think about what we may have done wrong in the implementation. Didn't think that we need to check that the ID was correct. Didn't think that we need to maybe forgot a condition with the app. Instead, we focus on minimal definitions and simple definitions of our API behavior. We define which actions exist on the API. We defined a small piece of state as small as we could, something simple, and we define behavior as the way the actions affect the API. What we got back from our hypothesis is fairly realistic bugs that contains more than a single API call, and thanks to the minimality of shrinking, the results were very easy to diagnose and debug. It was a couple of seconds to understand what happened. Another thing that happened is that while usually with tests we mostly find regressions issues, here we found completely new bugs in scenarios that we never thought of. Now, probability-based testing in general and stateful testing in particular help protect us from categories of bugs, not individual bugs. Why categories? So it's true that the tester found specific bugs. There are always specific bugs in the code. But the point is that the test didn't look for these specific issues. It found them because they affected somehow properties of the output. And this test catches with very high probability almost every bug that affects not the content or details of the books, but which books are in the list. So every unintended creation or replication or deletion or undeletion, and not going into the details, but turns out that you also can change accidentally an ID of a book without the test catching it. So we can say sort of that this test catches anything in the category of bugs that corrupt the list itself. How much work would it be to write standard normal tests that are as good as catching bugs? Catch almost every bug that corrupts the list of books. Try to think with yourself how much effort you think it would be. And I don't know what's the numerical answer that you come up with, but at least in my experience, the essential answer is that it's just too much. I mean, it's not that we can't write tests like these. We can, but in almost all cases, we just don't because it's too expensive. Now, the test that we saw here that caught all the bugs, that's a file with less than 60 lines of code. 60 lines. And it's not that it's 60 lines or 70 lines or 100 lines. It's not the point. The point is it's just not a lot of work. It's a few hours, less than a day. And it's true that it was a simple application because we need something simple to be able to see the test get built step by step in a talk. But the thing is that the relation between how much work we put in, how much we invest in writing these, and how good they are at catching bugs, the ROI. And I think this ROI is a good thing to have in your toolbox. couldn't fit the code for stateful testing in the presentation, but I did put in GitHub the repo not just for the full test, but every stage that you saw in the presentation here as a separate folder, and you can run it and see how it evolves. Okay, so we saw a few nice things that property-based testing can do for us. Now let's talk about the problems a little bit. And first of all, property-based tests are tests, so issues that are difficult to test in general are also difficult here. Testing code with a lot of side effects or a lot of dependencies or performance issues. And actually performance issues are even more difficult with property-based tests because we run a lot of test cases. So when it's slow, it's really slow. And the ways that we deal with it are the same as with the standard tests. Caching, test doubles to replace part of the system, stuff like that. A challenge that's specific to property-based testing is generating data or generating inputs. I won't dive too much into it in this talk, but usually it's not the most difficult thing, but sometimes it is a challenge and it's worth being aware of. The main challenge with property-based testing is finding properties to check. Let's say we have inputs that are good and diverse enough, but what do we check? What do we check on the outputs? It's not always trivial to find something that's actually useful to check. And let's look, for example, at a super simple function reverses a list. We can intuitively, maybe we would say intuitively, right, no problem. I'll just check that the two lists are reversed. Write an R-reverse function and check that the output is the reverse of the input function. Sounds good, but the problem with this is that checking if two lists are reversed, it's very, very similar code to the code for reversing a list. And that's not a good idea. The main reason it's a bad idea is that it tends to generate pretty weak tests, because if I've just written some piece of code and then I re-implement it slightly differently for the test, chances are, if I create a bug in the code, I'll also create the same bug in the test, and the test won't find the bugs. So we need ways to find properties that are good at catching bugs, are effective. And luckily, people have been writing property-based tests for a while and noticed quite a few things, techniques that help. We'll see a few examples, and these techniques got the main property-based testing patterns. So the simplest one is you run the code. Yeah, run the code, make sure it doesn't crash with valid inputs. And sorry, can you close the door, please? Thanks. Make sure it doesn't crash with valid inputs. It sounds silly, but it's surprisingly effective. We've all written, for example, log statements that crash because the string format was incorrect. Stuff like that, very good at catching them. Invariant. We saw with the sorting that the output of the sort contains exactly the same elements as the input. So there's some property of the data which elements are in the list, and the code doesn't change this property, it preserves it. Something like that is called an invariant, something that doesn't change. If the code preserves some invariant, it's probably a good idea to use it and check it, because invariants are very easy to check. Difficult to test, easy to verify. Like we saw in the sorting function, sorting a list might be complex, optimized, very, very interesting code, but checking that a list is sorted is trivial. We saw it, it's a for loop with 2 lines. Idempotence. An action is idempotent if applying it more than once has exactly the same result as applying it once. So the sorting a sorted list returns the exact sorted list. A real world system example might be charging credit cards, right? Maybe the client gets timeouts and sends like 15 retries, but we better only charge the credit card once in the server. Round trip. If our code has some action that reverses it, it helps us. For example, we take an object, we decode it to JSON, encode it to JSON, then decode that. We expect to get an object that's identical to the original object. This is very strong, difficult. Test worker. There are a lot of situations So you can model a system or part of the system or an algorithm with code that's a lot simpler, but still does the same thing logically. And the reason that it's possible is that the real code, the actual production code, needs to deal with a lot of stuff like authentication or performance or talking to distributed databases. But the test oracle doesn't need to do any of that. It just needs to return the same responses for short, simple, and fast test cases that easily fit in the memory of a single process. And this is a very useful idea. We'll see just a couple of examples. First, of course, with the sort function, we have easy ways to test it. We have other sort functions that we trust. So we can just test that it always returns the same thing as Python's default built-in sorting function. And in this case, it's a full alternative implementation, so the ROI is especially good. These 3 lines of code, that's a full test suite for sorting function. Right? It's almost impossible to write an incorrect sorting function that passes this test, these 3 lines of test code. The large example that we saw with the books, with the book list, with the stateful testing, and really any stateful testing is a variation on the test oracle. The idea of looking at the system and finding like some very, very small aspect like the number of the books and how the actions against the system can affect it. That's exactly the idea for test oracle. You've rewritten a service in a new technology, awesome. The old service is a test oracle for the new service. Just putting together one side by side and bombarded with hundreds of thousands of sequences of identical actions. Every time they return different responses, we found the bug. There are a few other ideas like these, or variations and combinations of the same ideas. The main takeaway is that we can, a lot of the times, find useful, effective properties to check, even if at the beginning it doesn't look promising. Okay, we had a small taste of running-based testing. My objective with the session is not just to introduce the subject, but also to help you get started. So, a couple of ideas that might help. First, take some simple probability-based tests and reproduce them. So, maybe download my repo with the sorting function and delete the properties and rewrite them. Maybe write some other properties that are not there. Just get the feeling for the mechanics of it, how it works. Having some simple weak test is much better than having no test. So write something, and a weak test can still be very useful, right? Even if you look at some very simple examples like this test suite, it's not complete, won't catch all the bugs, but it's already pretty strong. Just testing the sort is important, and a couple of examples, almost every mistake that you will make will be caught in a couple of seconds, right? It will make your life easier. And the most important thing about your first probability-based test is that you write it. So start with something easy. Your first test doesn't need to be the strongest test for your most important component. Anything you write strong tests, but just get started with something. What would be easy? Couple of ideas. Pure functions are a great example of something that's easy to test. Usually, pure functions are functions that are calculations machine, right? They receive an input, returns an output. Can check global state, can affect global state, can call the database, can change the input. They only calculate an output. Small API function that receives 3 integers is easier to test than a function that receives 4 complicated structures in 5 lines. And prefers something that doesn't have a setup, or maybe small setup, not 7 dependencies. And stateful testing is awesome, and you should do a lot of it, but it does have an extra learning curve, maybe not as your first test. And this is maybe less of a getting started tip and more of a general testing guideline, not just for probability-based tests. Don't try to test if the code is correct. Focus on a single aspect of the behavior of the code. So, like we saw with the book count, So that's something like that. We put something in a data structure, make sure it's there, add the stuff to the database, and maybe we have a latest function, so make sure that it does return the latest thing, or the largest or something. Check HTTP responses, make sure that the HTTP status is correct, stuff like that. Always start with these like very narrow questions. A single aspect of the behavior of the code. As promised, link with list of resources of the code, summary of the techniques we talked about, and also some other resources to help you get started and see other things. Thank you very much.